This is directly off your upcoming test, and I'd like you to notice the directions. These directions, the answer blanks and everything, are exactly as they'll appear on your test. Again, I want there to be no surprises. I want you to know exactly what my expectation level is. On this particular problem, I want to use just the first derivatives to find all the critical points of the function, and then the first derivative test to determine if those are maximums, minimums, or inflection points. You must show all your work in the space that I've allowed here on the test, and I want you to determine whether each region is increasing or decreasing. As you determine that, you'll simply circle the increasing or decreasing and state why you know that's true to the right in that answer blank. So with that given, let's go ahead and get started. First of all, here's my equation up here. F of x equals x to the fourth minus 2x squared plus 7. The first thing, of course, I have to do is take the first derivative. When I take the first derivative, that would give me 4x cubed minus 4x. Now at this point, I have to set that equal to 0. So 4x cubed minus 4x equals 0. Let's go ahead and factor out our common term of 4x, which will leave me with x squared minus 1. Continuing my factoring, I hope you notice that that is the difference of two squares. This is essentially x squared minus 1 squared. So my first one, my first binomial, I just simply remove the squares. So that's simply x minus 1. The second one will be exactly the same, except it'll be x plus 1. Now at this point I have the product of three things: 4x, x minus 1, and x plus 1. If the product of those three things equals 0, then either 4x must equal 0, or x minus 1 must equal 0, or x plus 1 must equal 0. In this case, x equals 0, x would equal 1, or x will equal minus 1. Now those are my critical points. At this point, I now know where my critical points lie. I have to determine what is going on, whether these are maximums at these points, minimums, or inflection points. Now, you folks have the advantage of actually being allowed to use your graphing calculator. If you're smart, at this point, you would have already plugged this function into your calculator, seen the graph, and you would know exactly what you're dealing with. I'm going to go at this blind because, again, the point of this examination, the point of what I'm trying to find out is, can you use the calculus to do this problem? In this case, I'm just going to draw a straight number line, basically representing the x-axis. And I've got a critical point here at -1. I've got something going on at 0. And I've got something going on at +1. And I basically have four regions now. 1, 2, 3, 4. On your test, you may or may not use all of these blanks. There may be one or two blanks that you won't have to use, depending on how many regions. I've purposely not given you a clue. I've tried not to tell you in advance how many critical points to expect. This particular problem, I have exactly the number of blanks, but don't expect that to be the case on your actual exam. So let's figure out what's going on over here in region number 1. Basically, I need to plug in some number less than -1 all the way to infinity. I always look for the easiest mathematical thing to plug in, so frankly, I am simply going to plug in a -2. That's a small, easy to use whole number, so hopefully the arithmetic will be pretty easy here. I merely plug that in to my function, and I find the value at that point is -24. So the first region, I know, since this is a negative value, that my function is decreasing. And I know it's decreasing because f prime of -2, a point in that region, is equal to -4. Now that also tells me, well, I'm sorry, I need to do one more step before I know that for sure. Let's take a look at a point in the second region. Now unfortunately, there are no whole numbers between -1 and 0. So in this case, I'm simply going to have to plug in a fraction. Let's plug in -1/2. And when you plug in -1/2 into the function, you find a value of 1.5. So I know my second region is increasing because when I put my value in, I got a positive 1.5. So my second region is increasing. My first region, I knew that it was going in this direction. My second region, I know it's increasing, and that tells me for sure at this point, at -1, I must have a minimum. So I'll put -1 over here in my minimum section. Now let's take a look at something from the third region. Let's look at a point between 0 and 1. Once again, there are no whole numbers. I will have to merely plug in 1/2 or some other fraction, but this is the easiest one to work with, into my first derivative. And when I plug that into my first derivative, I get -1.5. That tells me in this region the graph is decreasing because it's negative. So I'll circle decreasing for region 3, and I know it's decreasing because f prime of positive 1/2 is a -1.5. Now notice that also tells me that this point here at 0 must be a maximum. So I'll say over here at x equals 0, I've got a maximum point. Finally, I need to plug in a point here where I have a value greater than positive 1 in my fourth region. So again, I will plug that into my first derivative. Let's plug in a 2. Calculating the value, I find that that's positive 24. So, since the first derivative at x equals 2 gives me a positive 24, I know for a fact at this point, since it's positive, my final region is increasing. So I will circle increasing here in region 4. And this also tells me, by the way, that at this point, this must be again a minimum. So I'll put that up here in the minimum section. Now, one of the things I should have done that I didn't do was put my first derivative in my first answer blank. I'll go ahead and take care of that right now. There are no inflection points. If there was an inflection point, I would have to go ahead and take that x coordinate, plug it into my original equation to find out what that inflection point was. Now remember, an inflection point would only be a place where both sides of the point you're looking at are either increasing or decreasing. For instance, if this second region had actually been decreasing at this point, if it had been going in this direction, then I would know that this was an inflection point, because at that point it went down and then went down some more. So momentarily that first derivative must have been 0, which would tell you it was flattening out at that point and then continued down. At any rate, at that point I would have had an inflection point. I would have had to plug -1 into my equation to find out the y coordinate, and I would have had to put the coordinates of the point here in this blank. Now on your exam, inflection points are the only ones that I'm going to want the entire point. On the rest of the test, to save time, so you have more time to work on more problems, frankly, all I'm going to require for you when you have maximums and minimums is that you merely give me the x coordinate where those maximums or minimums occur. Let's take a look at our second problem. In this problem, I've gone ahead and used the same equation that I used the first time. The first part of the problem will be exactly the same. You still have to take the first derivative, set it equal to 0, and find all the places where the first derivative is equal to 0. That gives you all your critical points. But after that, the problem changes a little bit. On this problem, I'm going to want you to use second derivatives to identify the inflection points and to determine if these points were either inflection points, maximums, or minimums by using the second derivative. Okay, so let's go ahead and find the second derivative because I'm going to have to use that for everything on this problem. I've got the first derivative listed here. To find the second derivative, I merely take the derivative of my first derivative. This would give me 12x squared minus 4. Now there's no order you have to do these in, so let's begin by finding the values of my second derivative at these critical points to learn what they are. So if x equals 0, I know that my first derivative equals -4. if x equals -1, I know that my first derivative would equal +8. And finally, if I plug in a +1 into my second derivative, then I also get a +8. So again, plugging in the three values that I found, plugging in the 0 gives me a second derivative value of -4, plugging in the 1 gave me a value of +8, and plugging in -1 gave me a value of positive what? Excuse me, a +8. So up here, I know that my critical value at x equals 0, notice, was a negative number. Since my second derivative was a negative number, this absolutely tells me that I've got concave down. If I have concave down, then that must be a maximum of that point. I will merely circle maximum, and over here in my reason, I'll put because the second derivative at 0 was a negative value. For my second point, let's go ahead and put in -1. Again, I had a critical point at -1. At this point, my value was positive. Well, that means I have concave up if I have a second derivative that's positive, and that would indicate that the critical point that you had at the bottom must be a negative. So my critical point at x equals -1 is a minimum, and I know that because at that point, when I plugged in the -1, I got a +8. And finally, likewise, when I plug in a +1, I also got a positive value of 8. In other words, my second derivative, when I plugged in a +1, was also +8, and that would again indicate to me that this was a minimum. Now, the second derivative would have to be equal to 0, of course, for any of those to be an inflection point. So at this point, I've identified what was happening at all those critical points by using a second derivative test. Now, I'm going to find more inflection points in the second part of this problem by using my second derivative test. Now, let's go ahead and do that. And in this case, my second derivative test, I'll set my second derivative, copying that down again, equal to 0. The first part was a second derivative test. When you set the second derivative equal to 0, that tells you that you're at the point between which you have concave negative and concave up and concave down, which tells you have an inflection point. These may be additional inflection points to what we found when we were using the first derivative test. So let's take a look. Let's add 4 to both sides of the equation. By the way, you notice that I only have one squared term, so there's no point to factoring this time. You could factor if you preferred, but this is a much easier method since there is only one term with x in it. I'll divide both sides by 4, and I get 1/3. Taking the square root leaves me with x equals the square root of 1/3, or the square root of 1, which is 1, over the square root of 3. Now, I need you to notice as well that this could either be a positive value or a negative value when you take a square root, because either a positive or a negative, when you square it, would result in a positive 1/3. Now, this is the way I prefer the answer, but if you would rather list this answer in decimal form, that would be acceptable to me as well, but please round it to the nearest thousandth place for purpose of the test. And now what I need to do is find out what the value of the function is at these points. I need to go back to my original equation and plug in these values. So if I go back to my original function and I plug in a positive 0.577, I end up with a 6.444 for my y-coordinate. Likewise, if I plug in a negative 0.577, I also get a positive 6.444. Now, I'd like to point out to you that when I put these values into my function, I did not put the rounded value. Rather, I put the value in decimal form all the way back to infinity, and then rounded my answer to the nearest thousandth place. So I know that I have an inflection point at positive 0.577, and I apologize that I did not make the blanks big enough to accommodate my large marker here. They will be large enough for you on your test. Don't have any worry about that. So I put my x and y coordinates so that I have the actual point. This is my inflection point, and I know it's an inflection point because this was where the second derivative was equal to 0. And similarly, I had one at negative 0.577, positive 6.44 for my x and y coordinates, for the same reason, because I knew my second derivative was equal to 0. And that is how you use the second derivative in order to find what the critical points that you found using the first derivative were maximums or minimums, and how you use the second derivative to find your additional inflection points.